Welcome to the fourth lecture in cryptography on stream ciphers and pseudo-random generators. So to review, a cipher is defined over a triple of sets, a key space, a message space, and a ciphertext space. Is a pair of efficient algorithms E and D, encryption and decryption algorithms, such that for all messages in the message space and all keys in the key space, if we encrypt a message using a particular key and decrypt using the same key, we get back the original message. The only property that we need to satisfy is that encryption is the opposite of decryption. So some weak ciphers are substitution ciphers, Vigenère ciphers, and we established that the OTP is a good cipher. The message space here is the set of all n-bit binary strings. CT is the set of all n-bit binary strings, and the key space is also the set of all n-bit binary strings. So the way we encrypt is by simple XOR. To encrypt the message, we just XOR the message in the key, and that gives us the CT, and to decrypt the CT, we just do the XOR again, and that's easy to show by properties of XOR that in fact encryption is the opposite of decryption. So in the last lecture we established that the OTP has perfect secrecy, for example, that there are no CT-only attacks. There may be other attacks possible, but we can't do any CT attacks. If you're an eavesdropper and you only see the CT, you won't be able to deduce any information about the encrypted plaintext. So bad news about this is the following. Because the key length is as long as the message itself, transmitting the key when one could just transmit the message itself, right? So that's a problem. So we want to think about making the one-time pad practical. So an idea here is to replace our random key with a pseudo-random key, right? So stream ciphers. So we have a PRG, a pseudo-random generator, and we define it as follows. So a pseudo-random function is simply a function g for generator, which takes a seed. So I'm going to take 0 and 1 to the s in order to denote which we call the seed space. So we take the seed, which may only be 128 bits, and we expand it into essentially a much larger output string that could possibly be gigabytes long. So the goal is that the generator is efficiently computable. There should be some sort of efficient algorithm which computes it. So this here is called the seed space, all strings of length s, and it maps into a much larger string which we denote by 0, 1 to the n, with the properties that n must be much, much larger than s. So the function g itself has no more randomness in it. It is totally deterministic, and the only thing that's like random is the random seed that is given as input to the function g. So another property is the output should look random, and so then we ask, what does it really mean to look random? So we have a generator. How do we use it to build the stream cipher? So how do we use it to build our stream cipher. So we're going to use the seed as our key. So our short seed is going to be the secret key, and then we'll use the generator to expand the seeds into a much, much larger random looking sequence or pseudo-random sequence. Okay. So here's G of K. XOR it, the message, out comes the ciphertext. Then we are going to XOR the pseudo-random sequence with the message, and that will give us, of course, our ciphertext. So C equals the message M with a key K, which is simply defined as M XOR G of K. Okay, and then when we want to decrypt, we basically just do the ciphertext XOR G of K, just like in the OTP encryption, except instead of XOR and K, we XOR with the output of the generator. So the first question is, why is this secure? So we ask, can a stream cipher have perfect secrecy? So can a stream cipher have perfect secrecy? And so I want to just give you a moment here to think about it for a bit. So we decide no, the key is shorter than the message. So no, the stream cipher actually can't have perfect secrecy, because in a perfectly secure cipher, the key must be as long as the message, and therefore it is not possible. So why is it secure? We will need a different definition of security to prove that it is semantically secure. And in particular, the security property is going to depend on the specific generator used. So stream ciphers cannot have perfect secrecy. We need a different definition of security, and security, of course, will depend on a specific PRG. And we'll get into that definition in the next lecture.